There's a curious kind of heartbreak in something that you messed about with when you were a teenager coming into vogue when you're 40. But that has been my experience with AI. So I'm going to use that as a way of kind of giving a very quick synopsis of what AI entails in this presentation. A few aims in doing that. The first is just to kind of give a kind of a primer on basic AI concepts for the panel discussion. There's quite a lot of misinformation, quite a lot of misperception to do with artificial intelligence and how it gets used. And I want to kind of clarify that a little bit. Part of the misperception is to do with very elevated and very implausible claims being made about AI. I don't want to deflate those completely. To be fair, it has had quite a lot of kind of revolutionary impacts. So in that sense, you know, AI is what it promises to do, but we need to just be careful on how we tease out the implications of that. Just to give some indication, my name is James Carney. I'm Director of Texture Labs, recently rechristened as Texture AI to fall in with aforementioned Vogue. And that's kind of the background from which I'm speaking. It's academic as well as commercial. So the first step in doing this comes with looking at what it is about artificial intelligence that leads us to make some of the kind of typical mistakes we can make about it. And let's take a look at that. Are we back in this space?
The other clicker?
Other clicker. Oh yeah, Barbican. No, we're okay, we're okay. So yeah, that's me. Yeah, it's just a bit of a lag. So let's look at the two terms that make up the acronym artificial intelligence. The first problem is the word intelligence. Though we have all got a very good intuitive sense of what intelligence is and how it works and what it does, it is a very, very difficult term to nail down in precise terms. For at least maybe 150 years, cognitive psychologists have been trying to arrive at a working definition of intelligence and what it is that intelligence does. And while we have some kind of fairly kind of, we have ways of doing that. You can define intelligence as how you perform at basic reasoning tasks with respect to logic, spatial ability, and verbal reasoning per unit time, standardized by population. Those particular definitions aren't particularly good at capturing our intuitive sense of intelligence. A lot of the tasks used to design or used to measure intelligence in things like IQ tests are very formulaic, and they're very, very easy for an algorithm to perform. My phone can do Sudoku, for instance, in orders of magnitude faster time than I can. Does that mean my phone is more intelligent than me? You know, let's put that out there. So, you know, there's a sense in which intelligence is very hard to define, very hard to measure. And my point in raising that is that it's freighted with so many associations that it's quite difficult to disentangle those associations when we come to think about AI and when we come to talk about AI. The second problem, by process of implication, is to do with the word artificial. We've been conditioned by decades of science fiction to have a certain set of associations with artificial, and especially artificial, when it's predicated against a term like agency or intelligence. We think of artificial agents as being like human agents, but with small differences. In cognitive psychology, that's known as positing a minimally counterfactual or counterintuitive representation. And we are addicted to minimally counterintuitive representations. We think of singing dogs, we think of weeping statues, we think of virgin births. Our whole culture is centered upon these basic ideas, which are like concepts that we are familiar with, but which have a very small difference attached. And AI tends to attract these kind of minimally counterintuitive representations in all sorts of ways. And you can, okay, the clicker that worked, oh, here we are. So the science fiction aficionados, of which I'm sure there's one or two in the audience, will recognize this as a frame from the first Terminator film. And it represents the kind of internal view of the Arnie kind of cyborg who travels back in time to kill John Connors, or Sarah Connors in this case. And I asked, you know, when you look at this, you see pretty much everything that's wrong with our cultural thinking about AI manifest in a single image. Why would a cyborg have its own thoughts represented to itself in language on a scene that it can see? It's like saying you don't know your own thoughts unless they're written out for you to see them first. It makes no sense, and it makes no more sense in the context of AI than it does in the sense of our own intuitive sense of how we think as well. And it all leads to a fundamental point, a very important quote here from Edgar Dijkstra, a very famous computer scientist. And he said, the question of whether a computer can think is no more interesting than the question of whether a submarine can swim. And the point, of course, being is our intuitions are systematically wrong when it comes to artificial intelligence. And we need to be very wary of the kind of judgments we make and the easy cognitive leaps that we're prone to kind of fall into when we think about it. And we can come back to that a little bit later. So with that warning, that proviso in mind, what I want to do now is very quickly run through some of the basic types of artificial intelligence, how the field gets carved up. And there's lots of ways to do that. Like any kind of term of art, artificial intelligence can be cashed out in all sorts of different ways. And no two cognitive scientists or no two people who work in artificial intelligence are going to agree on the exact way in which the field gets partitioned. Some will say machine learning is part of artificial intelligence. Others will say it isn't. But as good a representation as any comes from Robin Goodfellow's relatively recent book on deep learning. And he gives kind of a nested set of diagrams or a nested set of Venn diagrams which show how the different types of AI relate to each other. And the point being is that each of them is hierarchically linked to the one in which it's embedded. So as you work from the outside in, each of the inner ones often draws upon what you have on the outside one. So to just start at one of the first manifestations of artificial intelligence is expert systems. Expert systems emerged in the 70s and the 80s as essentially what were known as ontologies or structured bodies of knowledge, where a particular area of expertise, say for instance medicine, is represented as a series of structured representations. But the structured representations aren't all that's there. What you also have is a series of inference generators or rule-bound queries that allow you to make new judgments on the basis of what's in the expert system already. And the point being is that the expert system doesn't have all the answers pre-programmed into it. It allows you to come at new data and new information on the basis of rules and chains of inference and reasoning that are there. A pretty good example of an expert system that we use every day is Google Maps. Google Maps has not pre-calculated the best route between every single 2 points in the world, but it has given the algorithm the information to do that. So as a result, you can arrive at new information on the basis of an expert system that comes pre-packaged with this structured information. The next one in then is machine learning. Now, machine learning is the term du jour. Every day we're looking at some new headline about machine learning and what it does. Logistic regression is just a specific implementation of machine learning. You don't need to worry about the details there. And the specific manifestation of machine learning that Goodfellow and his colleagues are talking about here is what's known as supervised machine learning. And in supervised machine learning, you have two things. You have a set of labels and you have a data set. And what happens is you get someone, typically a human being, to pair up the labels with specific observations in the data. So you have then your data set, and you have your labels, and you have the two correlated. What you do then is you train your model on that particular operation. So if you're using logistic regression, you train your model to figure out whether something is true or false, whether it's present or absent. And that's binary logistic regression, technically. But and what you do then is you train your model on this. And the model learns from all of these specific instances you've given it, so that when you present it with new instances, it's capable of saying what class the new instance belongs to, what label should properly be apportioned to it. And as I said, that is where most of the kind of commercial implementations are happening now. Not all of them, but a lot of them, and a lot of the academic implementations too. So machine learning, as I say, term du jour, we're all reading about it every day in the newspapers. The next one then, representation learning. That's sometimes known as unsupervised machine learning, as distinct from supervised machine learning. And this is where things start getting kind of clever, Because what happens in representation learning is you're giving an algorithm a data set which doesn't have labels. It's not pre-structured for the algorithm to understand. And what the algorithm does is it gets the huge amount of dimensions in this data set and it maps them down into a smaller number of dimensions. It figures out the important features, the important drivers, the important variables, and it learns what they are. And in representation learning, as I say, it's quite clever because this gives you back something you would not necessarily have found in there yourself. And because it's a machine implementing this and not a human being, it's performed at scale, it's performed with speed, and basically it outclasses a lot of what human beings can do in the way that it figures out these important aspects of a given data set. Machine learning, or artificial intelligence then in its kind of purest form, and perhaps in the form that most people understand it to be, comes in the form of deep learning. And MLP stands for multi-layer perceptron networks there. Again, you don't need to specifically worry about the details of what they are. But the key point in deep learning is that it's like taking any of the previous models and stacking them on top of each other. And it reflects kind of how the human brain operates as well too. When I look at something, the first thing that happens is my brain figures out the edges and the corners. And then it feeds it up to my cortex, and my cortex will try and go back and fill in, let's say, textures and shapes, and fill in further detail. And maybe I might discover that I'm not looking at an edge, I'm looking at something else. And then I go back down to the fundamental level again, and I do a second take. And the point is, you have all of these stacked up levels of processing, and they feed forward and they feed backward into each other. And that is the key architecture of deep learning. You'll be familiar with it perhaps from Google's DeepMind, which last year scored some stunning successes in the game of Go against expert opponents. And this is where the scary stuff is happening. Even just again last year, Google implemented some deep learning algorithms with respect to Google Translate. And the increases were quite stunning. So in the sense of what AI is, and in the sense that we kind of typically culturally understand it, deep learning is where it's at. But representation learning and machine learning are probably the kind of the bread and butter of the enterprise, if you like. And that in a very, very kind of rough and ready sense is a sketch of the AI landscape. It's not as neat as that, but it's as good as any map as you'll find. But the important thing to kind of remember, though, with all of this, is that the technical specifics only get you so far. There's an adage in artificial intelligence, which is that a good algorithm is always beaten by good data. If you have bad data, you will get bad results. And these are the kind of bad results you get. So you might have seen this last week in The Guardian, where a particular Instagram basically used this particular tweet in an ad. And the point is that the algorithm mistook valence. It assumed that a lot of shares and a lot of likes, it assumed that that was a positive thing. It confused arousal for valence. Two different measures of how human beings react to stimuli. And the point is that's bad data giving a bad result. The algorithms are only as good as the information that you feed into them, and only as good as the specific structure that is there in that data. It is not magic. It's garbage in, garbage out, GIGO, an old acronym from programming. And it's really crucial to remember that when you're dealing with artificial intelligence, when you're dealing with machine learning, 99% of the effort is getting the data into a usable form, which you then train your model on. It's very easy for us to get captivated by very clever algorithms that do incredibly smart things. But ultimately, the heft, the heavy lifting, the actual reason why this whole AI revolution is coming about is because, first of all, there was a data science revolution. And it became possible to get huge bodies of data, which you could then train the models on. The models themselves are, to my mind, somewhat less important than the data they're trained on. So with that caveat in mind, I'll leave it there and hand over to Maria.